This is Dr. Shankaraiah from Department of Physics. In this presentation, I am going to discuss definition and terminology on Module 4, which is magnetic and superconducting properties. Define a magnetic dipole. The two equal and opposite poles separated by a distance are constitute a magnetic dipole. Similar to electric dipole, we can define magnetic dipole as two equal and opposite poles separated by distance r. Okay, so you have south pole and north pole. The distance between these two is r. So that is a magnetic dipole. What is magnetic flux? It is defined as the amount of magnetic lines of forces passing perpendicularly through unit area of a given material is defined as magnetic flux, and it is denoted by pi. Okay, so how many magnetic lines are able to pass through a material is called magnetic flux. Recall the term intensity of magnetization. The magnetic moment per unit volume is called as intensity of magnetization. Define magnetic induction. Magnetic induction at a point is defined as the force experienced by a unit north pole placed at that point. That is denoted by B. Magnetic induction B is nothing but pi by A, number of magnetic flux lines per unit area, or you can define it as the force experienced by a unit north pole at any placed at that point. Okay. What is permeability? Permeability is the ability of the medium to pass magnetic lines of forces through it. So permeability is denoted by mu. Define magnetic susceptibility. It's defined as the ratio of intensity of magnetization and applied magnetic field. So magnetic induction is directly proportional to the applied magnetic field. So to remove proportionality, I am going to put a constant B is equal to mu chi h. Okay. So B is equal to mu h, or M is proportional to h, or M is equal to chi into h. So chi is actually M by h. Intensity of magnetization and applied magnetic field. So there is a ratio between these two quantities is susceptibility. Define relative permeability. Relative permeability is defined as a ratio of permeability of medium. So mu r is a relative permeability, is defined as permeability of medium mu divided by permeability of free space. So mu is by mu naught is mu r, relative permeability. So from this equation, you can also write mu as mu naught into mu r. Describe the magnetic permeability of free space. The magnetic permeability of free space is a measure of amount of magnetic lines of forces passing through the air medium. So it is defined as a ratio of magnetic induction field strength of free space to the applied magnetic strength. So magnetic induction field strength of free space to the applied magnetic field strength is magnetic permeability of free space. What is retentivity in hysteresis? The retentivity of a specimen is a measure of the magnetic flux remaining in the specimen when the magnetizing force is removed. So magnet BH curve in hysteresis curve is B versus H. So I apply magnetic field. As I apply magnetic field, there will be magnetic induction rise and it reaches saturation. As I remove the field now, the magnetic induction will decrease to a finite value, and this is called the ability of the material to store this residual magnetism is called retentivity. Define coercivity. The coercivity is a measure of the magnetic intensity required to destroy the residual magnetism of the specimen. Okay, so we know what is so applied magnetic field, magnetic strength. So I apply field, magnetic induction increases. I remove the field, magnetic induction decreases to a finite value. There is a residual magnetism, and then I change the direction and apply. So magnetic induction will go to 0, and this is the amount of field. So this is also H. So as I apply field from 0 to this much, this is the amount of field that is required to destroy this residual magnetism. So that is called coercivity or coercive force in hysteresis curve. What is magnetic moment? Magnetic moment is defined as magnetic strength and orientation of a magnet or other object that produces a magnetic field. That is magnetic moment, and magnetic moment generally we write it as mu m. Okay, mu m magnetic moment, which is product of current into area of the coil, so I into pi r square if we take a circular coil. Okay, so that is magnetic moment. Which magnetic material has high retentivity? The steel retains the magnetic field effect longer than the aluminum, steel, nickel. Okay, so steel is the best one compared to aluminum, nickel, and other soft iron, and therefore steel has the highest retentivity of the substance among the aluminum, nickel, and other materials. So steel will have highest retentivity. What is called retentivity? The property of the magnetic material to retain magnetism even in the absence of magnetizing field is known as retentivity or remanence. Which material has low retentivity? Electromagnetic materials are generally made of soft iron, so it is because they acquire magnetic property quickly, and as soon as the current flow stops, the material stops behaving as an electromagnet. So this indicates that the material has low tendency to retain the magnetic properties, and hence it is low retentivity. So electromagnetic materials will have low retentivity, and steel has the high retentivity. Define paramagnetic material. Paramagnetic materials are metals that are weakly attracted to magnets. They include aluminum, gold, and copper. Define ferromagnetic materials. Ferromagnetic materials are permanent magnets or solids attracted by permanent magnet. Define hysteresis loop. The hysteresis loop shows the relationship between the magnetic flux density B and the applied magnetic field H. That is hysteresis. What is meant by hysteresis loss? The hysteresis loss is the energy entrapped in magnetic materials exposed to a magnetic field in the form of residual magnetization and lost as heat during the demagnetization step. So, in the hysteresis, we apply magnetic field and in this direction, and then magnetic induction will increase. As I will remove, it will decrease. As we reverse the direction of magnetic field, again it will go to zero. So there is a energy loss in the material when we apply magnetic field and change the direction of the magnetic field, and so the energy loss is it will come out as heat during the demagnetization step. What is meant by BH curve? Hysteresis curve is a graphical representation that describes the magnetic properties of material. What is Bohr magneton? It is defined as the magnetic dipole moment associated with an atom due to the orbital motion of an electron in the first orbit of hydrogen atom. So this is the Bohr magneton. It is the this is the smallest magnetic moment so one can have. So Bohr magneton is the unit of the smallest magnetic moment of electron. Define superconductivity. So the phenomenon of attaining zero resistivity or infinite conductivity at low temperature is known as superconductivity. Okay, so yeah, so I am plotting resistance versus resistance versus temperature. So this superconductivity is that when we cool the material, the resistivity will decrease, and suddenly at certain temperature called critical temperature, the resistivity goes to zero. So okay, so this phenomenon is called as superconductivity. And for highly purified mercury, it is around 4.13, I think, Kelvin. Mention any two properties of superconductors. Superconductivity is a low temperature phenomenon. The transition from normal state to superconducting state occurs below Tc. Any two properties. So, okay, critical temperature and critical magnetic field. So, these are the two properties of superconductors. Okay, critical temperature. When we cool the material, for example, mercury below Tc, only then you will see the resistance goes to zero, and the transition temperature below which you have zero resistance, that is called critical transition temperature. Similarly, when you apply magnetic field above certain magnetic field H greater than Hc, you will see the superconducting state will be destroyed and the material will go to normal state. So, critical temperature and critical magnetic field are two properties of superconductors. Zero electrical resistance is another property of superconductor. Okay. So these are some of the properties. Describe the critical magnetic field. Yeah, so just now we have discussed when a magnetic field is applied to superconductors, then for a particular value of applied field, it loses superconductivity and becomes a normal conductor. So the magnetic field for which a superconductor becomes a normal conductor is known as critical magnetic. What is Meissner effect? when a material makes the transition from the normal to superconducting state, it actively excludes magnetic fields from interior. This is called as Meissner effect. Okay, so Meissner is the first scientist to observe this effect in superconductors. Okay, so when the material, so if we take a superconducting ring, so this is a superconducting ring, and this is in the superconducting state. For example, because we have cooled this ring to below Tc, so it has gone from normal state to superconducting state. And if we apply magnetic field to this superconducting ring, okay, we are applying magnetic field to this superconducting ring, then what happens? This this superconducting ring will exclude, this superconducting ring will not allow the magnetic flux lines to pass through it. It repels the applied magnetic lines, so it will repel. Okay, so the this phenomenon where the superconducting material repels the applied magnetic field is called Meissner effect. Okay, so based on Meissner effect, we have maglev trains, magnetic levitation trains, where the trains will float in air. Okay, so discuss energy gap in a superconductor. The energy gap between superconductors and semiconductors is a measure of the difference in energy required to excite an electron from its ground state to a higher energy state in the material. Okay, so superconductor has a very small or zero energy gap, while semiconductors have a larger energy gap compared to superconductors. This allows superconductors to conduct electricity with zero resistance, while semiconductors have some resistance. Define type 1 and type 2 superconductors. In type 1 superconductors, when the magnetic field is equal to the critical field, then immediately it converts to normal conductor. In type 2 superconductor, the applied field reaches low conversion start and it is completely slowly at after critical field. Basically, so type 1 superconductor has a sharp transition from normal state to superconducting state. So immediately it will be so below Hc it will be in superconducting state, and at Hc it will go to a normal state. Resistance is 0 below Hc, and at Hc the resistance will become a finite value. So the sharp transition from superconducting state to normal state is very sharp. Sharp transition from superconducting state to normal state. This is type 1. And in type 2, you have two critical fields. So there is a gradual transition from superconducting state to normal state. So gradual transition. So there will be a superconducting state in the beginning. At Hc1 you have two critical fields here. So at Hc1 slowly the resistance will increase, and it will reach a saturation value at Hc2. So you have superconducting state, and you have a normal state, and in between you have mixed state. Okay, so type 2 superconductors have three states: superconducting state, normal state, and in between there is a mixed state between critical fields Hc1 and Hc2. What is BCS theory? The properties of type 1 superconductors were modeled successfully by the efforts of Bardeen, Cooper, and Schrieffer. The theory, this is a quantum theory developed by these three scientists, Bardeen, Cooper, and Schrieffer, and hence it is named as BCS theory, that explains successfully the zero electrical resistance and Meissner effect of superconducting. Write any two applications of superconductors. Superconducting materials are used for producing high magnetic fields with low power consumption. First property. Diamagnetic property of a superconductor is a basis of magnetic levitation. So this effect can be used for high speed transportation. So yeah, perfect diamagnetism of superconductor can be used in maglev trains. So there is another application of superconductors. Why is a superconductor called a perfect diamagnet? Superconductors are ideal diamagnets. When they positioned in an external magnetic field, they repel the field lines from the interiors depending on field intensity and temperature. So diamagnetic materials are the ones which repel the external magnetic field. So superconductor also repels the magnetic field like diamagnet. So that is why we call superconductor as a perfect diamagnetic material, because they also repel the applied magnetic field above a certain critical fields. What is the role of superconductors in technology? Engineers use superconductivity in magnets to make ultra strong magnets needed in MRI machines. They have used superconducting conductive magnets in levitated trains, maglev trains. Okay, so not elevated, so levitated trains. Superconducting circuits allow for fast computer performance. So this is magnetic levitation, maglev trains. So magnetic levitation. Okay, because of this Meissner effect, we can use the property of diamagnetism of superconductors in maglev trains. So these are some applications in technology. What is magnetic effect? Magnetic effect of electric current means that an electric current flowing in a wire produces a magnetic field around it, and iron, steel, nickel, and cobalt is with the same. What is the cause and effect with magnetic field? When north and south poles of magnet are placed near each other, the different charges are attracted. Write some popular examples for superconductors. Some popular examples of superconductors: aluminum, magnesium, diboride, niobium, copper oxide, yttrium, barium, and iron. What is superconductivity used for today? Superconducting materials have been used experimentally to speed up connections between computer chips. What are two types of superconductivity? Type 1 superconductors, which totally exclude all applied magnetic field. Type 2 superconductors, which totally exclude low applied magnetic fields, but only partially exclude applied magnetic fields. So the diamagnetism is not perfect but mixed in the presence of high field. What is the origin of magnetic moment of nuclei? The nuclear magnetic moment is the magnetic moment of an atomic nucleus and arises from the spin of the protons and neutrons. What is magnetic origin? Magnetism originates from the spin and orbital magnetic moment of an electron, spin and orbital motion of electron. What is Meissner effect of a perfect conductor? In perfect conductors, the interior magnetic field must remain fixed but can have a zero or non-zero value. In real superconductors, all magnetic flux is expelled during the phase transition to superconductivity, and the magnetic field is always zero within the bulk of the superconductor. What is the principle of Meissner trapping? A Meissner trap is essentially a coil of tubing through which a gas or liquid cryogen flows to maintain a low surface temperature. That is Meissner trap. What is the critical current of a superconductor? The maximum electric current density that a given superconducting material can carry before switching into normal state is called as critical current of a superconductors. So these are the definitions and terminology in module 4. These are some textbooks used and references books. And to summarize, I have discussed the definition and terminology module 4, which is magnetic and superconducting materials. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.